Hi, we're continuing section 3.1, and in this section we're talking about level curves and level surfaces, ways of decreasing the dimension required to represent a function graphically. So typically the number of dimensions required to graph a function is equal to the number of input variables plus one dimension for the output variable. For example, we plot functions at y equal f of x in the plane, right? There's an x input and a y output, two variables, so we plot them in the plane. Functions like z is equal to f of x, y, we plot in three-dimensional space, x, y, and z. So how should we plot a function of the form w is equal to x, y, f of x, y, z? Well, we would need 4 dimensions, and I don't know about you, but my 4-dimensional drawing skills are a little bit rusty. So reducing the number of dimensions required to represent a function graphically is important. While we did in the last section, we represented with a color map z is equal to f of xy as a 2-dimensional plot instead of a 3-dimensional plot. That's useful, but representing the function w is g of x, y, and z in a lower dimension is essential. It means that we can do a 4-dimensional plot, which would be impossible without some sort of graphical animation. We can do this graphically in 3 dimensions with a perspective drawing. So let's go and read definition 3.1.3. The level curves of a function f of 2 variables are the curves with equations f of xy is equal to k for some constant k in the range of f. Similarly, level surfaces of a function g of 3 variables are surfaces with equations g of x, y, and z equals k for some constant k in the range of g. Let's go and look at the 2 images that we have here in figure 3.1.2. Let's look at the first one in A. Level curves on a function z is equal to f of xy, and a new word, a contour plot, which we'll talk about in just a second. Level curve, so we're saying that we're taking z is equal to f of xy is equal to k, some constant. So if we pick a constant value of z, if we pick a z value, I don't know, maybe here, and we take all the z values on the surface that are of the same height, then we are getting those f of x, y values that are equal to k. So we are getting all the points on the surface that are at the same level. Hence the name level curves. And for example, if we took another value of k, let's say k1 or k2 down here, this is k2, then those values are when f of x, y is equal to k2. So we have all the values, all of them, right? I guess these guys as well, where f of xy is equal to k2. And the same way that we were talking in the previous section, there's no point in drawing these curves on a 3-dimensional surface. The whole point of them is to be able to reduce the dimension. So here in the diagram, they have been projected up, but they could just as easily be projected down onto the xy plane, and you get these curves plotted all together. So there's our first and our second set of curves here. Those different values represent the different levels on the function surface. And so this is 1 dimension down. We don't need, if we've got these curves, we don't need the x, y, and z axis. We can do just with the x and y. And we look at everything here. This you might recognize. This actually looks like something that if you've been to a national park or you've been out in the wilderness and you've been reading a map, this makes us think of topographical maps. Mountain ranges and that sort of thing are very often shown in a flat map with these level curves or level curves. That's what they are. So when we plot all of these curves together on a single set of axes, so that is called a contour plot or a contour map. It's a two-dimensional plot of all the level curves of a function of two variables for, and this is something I didn't mention before, equally spaced values of k. You see in the diagram here, the height difference between those k values is always taken to be the same. That amounts to, the remark here, looking at level curves is essentially the same thing as looking at the curves of intersection of the graph of xy and the planes z equals k, just like we did when we were analyzing quadric surfaces. Now we've ignored part of the diagram here. What's this? This is a representation on the right here of level surfaces of a function w is equal to f of x, y, z. What that is all the points. So for example, all these points in red here, all these points in red are all x, y, z points, right? The domain of a function g of x, y, z, or f of x, y, z is 3D points. All the points x, y, and z where the function has the same value. Has the same value k. And then you've got, right, different levels, different level surfaces, right? This is where w is equal to some other value k2. And these graphs, if you project them down, well, you're projecting them down from 4 dimensions into 3. The analogy of what we did here, we projected from 3 dimensions down into 2. So this is the projection down into 3 dimensions. Right? We can imagine a set of axes down into R3 here from 4 dimensions, which I cannot draw. But this is the projection down into 3 dimensions of a function in 4 dimensions, representing the level surfaces. All the sets of points where the function has the same value, they will form surfaces when the function is a function of 3 input variables. In the next video, we're going to do some examples where we come up with these level surfaces and level curves ourselves.